Continuing on with what happens when stars die, we are officially going to talk about my favorite thing in space. Aliens are cool, rocks from the moon are cool, but black holes, they break science. They legitimately break the rules of physics. So we're going to take a look at why a black hole happens. First, what is it? Why it happens? Are there different types of black holes? How big are they? And then what everybody wants to know, what happens when you fall into a black hole? Are they ever going to go away? How long do they last? We're going to cover a lot of stuff. So let's get started. Starting off with what is a black hole? It is a supernova remnant, most of them are. It has a very large mass with zero volume. It has zero volume because there's nothing that can push back out against gravity. So it just keeps getting smaller and smaller and smaller until you get to an infinitely small point. If you know density, it's mass divided by volume. And if your volume is zero, and you have a zero in the denominator, and you press enter on the calculator, it returns an error. This is breaking science. We don't know what happens at the center of a black hole. Let's get that out of the way right now. We can guess, we can make conjectures, but we don't know what is going on at the center of a black hole because the laws of physics that we can study and see and understand break when you get into a black hole. And so there's no way for us to know without traveling there. And if we travel there, we can never come back out. We can never even send out a signal. So there's really no way to know what's happening inside of a black hole. Obviously, they have extreme gravity. The key to a black hole is that the gravity is so strong that its escape velocity is faster than the speed of light. Now, what do I mean by that? If you throw a ball up at 5 meters per second, it's going to go a certain height. If you throw it up at 10 meters per second, it's going to go a little bit higher. If you throw it up at 100 meters per second, it's a little bit higher. Depending on how much gravity you have, there's a certain speed that you have to reach in order to escape the gravity of that object. For Earth, it's about 11 meters per second, but you have to sustain that 11 meters per second as you're escaping Earth's gravity well. Well, if you add more mass, you have to travel faster to escape the gravity. More mass, you have to travel faster. The bigger the object, the faster you have to be able to travel away from it to escape its gravity. A black hole has so much gravity that the speed that you have to travel to get away from it is faster than the speed of light. Nothing can travel faster than the speed of light. It's the hard stop speed limit of the universe, which means nothing can travel fast enough to escape a black hole. You literally cannot get out of a black hole. Black holes have two parts. The first part is what's known as the Schwarzschild radius. If you remember, Schwarzschild was the guy in that photo with Anja Hertzsprung that I showed you a few weeks ago. Anyways, so the Schwarzschild radius is the area around the black hole that you cannot escape from. If you have a sphere with the radius of the Schwarzschild radius, we would call that the event horizon. Once you travel inside of that Schwarzschild radius, you cannot get out. The other part of the black hole, that's the singularity. That's the center. That's where the mass is located. That is what breaks science. The singularity is at the middle, and we have no clue what that looks like. What's going on at the singularity? That is that infinitesimally, it's a hard word. That's a really small point. So the event horizon is just the area around that singularity. The singularity is kind of technically the black hole itself. That's where all the mass is. And then the event horizon, or the Schwarzschild radius, that's going to be the area around it that you just can't escape from because you are traveling towards that singularity. So when we talk about the size of a black hole, what we're doing is talking about the Schwarzschild radius. But in reality, the actual matter is all condensed at the singularity. So there's two parts to a black hole. There's the area of space, area of space-time, that is affected by that black hole, and you can't leave it, the event horizon, if you will. And then you have the singularity, which is where all of the matter is located, that's all smushed down together. Why does this happen? Well, if you remember, at the core of a star, when you run out of material to fuse together, and you cannot push outwards anymore, gravity is going to start pulling everything in. When a star like our sun runs out of material, it's going to pull everything in until the electrons are pushing back out. That's electron degeneracy pressure. If you're a little bit bigger, you collapse down and you push those electrons into the protons, turning them into neutrons. And then the neutrons cannot be in the same energy level as another neutron, the same area of the universe, which forms a sort of pressure that pushes out against gravity. That's known as neutron degeneracy pressure, where the neutrons can't get any closer because it would break the rules of physics. Well, if you have enough mass, you have enough gravity to take one neutron and push it into another neutron. You have enough gravity to break the Pauli exclusion principle, to break the rules of physics. You literally are taking one particle and you are putting it into another particle. And we don't really know what happens when you do that. We can calculate that that can happen, but if you take all of those neutrons and just push them into each other, you then have nothing left to push out against gravity, and gravity is going to make you even tinier and even tinier, and that's how you get down to that infinitesimally small singularity with a volume of 0. Anything in the universe can become a black hole. All you have to do is smush it inside of that Schwarzschild radius. So if you take an object and you condense it down and keep compacting it and getting the particles closer and closer together, you're going to get past that electron degeneracy pressure. You're going to get past that neutron degeneracy pressure, where the neutrons are now in the same area. So if you took planet Earth and just kept smushing it down to about the size of a peanut, the particles in our planet would be in the same part of the universe, the same area of space-time, and you would then create a black hole. The Earth would be dense enough to be a black hole, where the escape velocity is faster than the speed of light. As long as you take that object and get it smaller than the Schwarzschild radius, you create a black hole. If you took me or you and smushed it down to that many inches, roughly the size of a proton, then we would be dense enough where light cannot escape. All of our particles would be in the same part of the universe, and we would be a black hole. A very tiny black hole, but we would be dense enough to be a black hole. So the Schwarzschild radius not only tells you where that event horizon is going to be located, but it also tells you the size that you need to smush something down to in order to turn it into a black hole. A lot of people are worried that Earth could possibly get sucked into a black hole. They're just all over the place, traveling around our galaxy, sucking everything into it. That's not what happens. Remember, a black hole, most of them come from a star. So if we were not being pulled into Betelgeuse, well, when Betelgeuse goes supernova and becomes a black hole, we're not going to get sucked into that black hole. You only have to worry about falling into a black hole if you are very close to it. Just like if you were very close to a star, you would get sucked into the star. So a black hole is just an object that has a bunch of mass, so it warps space-time, and if you get too close, you're going to fall in. It's not like a black hole is this magic thing that can pull things from across the galaxy into itself. It doesn't work like that. If a black hole is in completely empty space and there's nothing around it to fall in, then nothing is going to go into that black hole. That black hole is just going to kind of sit there. However, if the black hole does have other stars or nebula or other things around it, then yeah, when they get close, that stuff is going to start falling into the black hole. And if that's the case, what's going to happen as things fall in, it's actually going to start to orbit around the black hole, and that orbit will get smaller and smaller and smaller, and we call that an accretion disk. And this accretion disk are things that are falling into the black hole, and over time, that orbit is going to decrease, and it's going to get closer to the black hole until it passes this line, the innermost stable circular orbit. Once that happens, you're inside of the event horizon. You cannot leave. A lot of people ask what these jets are that are shooting out of a black hole. If nothing can escape a black hole, then what the heck is this? Well, these are basically particles that are falling into the black hole, which has a very strong magnetic field. As things are falling into the black hole, there is a lot of friction, and so they heat up and they become ionized, which means they also respond to magnetic fields. Well, a black hole as it spins, creates a very strong magnetic field. As these ionized particles fall into that magnetic field, many of them are going to get slingshotted out of the north pole of that magnetic field. Others will get slingshotted out of the south pole. These jets have particles going a very high fraction the speed of light. And those particles were saved, if you will, because they were slingshotted out just before crossing that event horizon. Had they crossed that event horizon, there's no possible way that we know of that they would ever be able to get out. That's where these particle jets come from. Now, how big are black holes? There's really no limit. Any amount of mass can technically turn into a black hole. You guys could be a black hole if you could find some force that could smush you down inside of the Schwarzschild radius. Most black holes are produced when a big star goes supernova, so we think that the mass of most black holes are roughly the mass of a big star, because all of the matter in that black hole comes from that big giant star. A typical black hole might be about 10 times the mass of the sun, which isn't actually anything too crazy. However, at the center of galaxies, you have what are known as supermassive black holes. One of the things that helps keep all of the objects in the galaxy kind of together. The reason these are so big is because at the center of a galaxy you have a lot of material, a lot of stars, a lot of gas, a lot of dust, and that black hole is going to start having some of that stuff fall into it. The more stuff that falls into it, the bigger the black hole gets. The bigger that black hole gets, the more space it takes up. So its mass and its Schwarzschild radius are directly proportional to each other. A black hole with about 1 solar mass would have a Schwarzschild radius of about 3 kilometers. So 10 times the mass of the sun would be about 30 kilometers. 1,000,000 times the mass of the sun would be about 3 million kilometers. It is directly proportional. If I double the mass, I double the size. And for reference, this is that jet of material shooting out of the supermassive black hole at the center of this galaxy. This line right here is 88,000 light years across. Our Milky Way is only 100,000. So this line is roughly the same size as our Milky Way galaxy. And you can see that the galaxy might be smaller than ours, but those jets from the black hole at the center travel out to maybe almost 2 times as big as our entire galaxy. Those jets are absolutely huge. How do we know that they're there? If we can't see them, they don't give off any light, how could we possibly know that they're there? Well, here's a photo of one. Take a look at this nebula about 55 million light years away, and you zoom in, and you zoom in, and you zoom in. We've actually got a photograph. This is a photograph that came out a few years ago, and what you're seeing, this bright area, is the accretion disk. The black hole itself is actually not this entire area here. It's the actual event horizon is going to be a little bit smaller. This accretion disk, though, is glowing because the material is heating up, and we are actually able to see it in X-rays because that material gets so hot. Most of the light,
currently the only person in this conference.
Most of the light that comes out of it is going to be in the X-ray part of the spectrum. You can see it better with this artist's rendition, which is what's been going on over my head. And you might think, looks kind of weird if an accretion disk is just basically like a big hula hoop. What is all of this stuff going up and down? Well, that accretion disk is just the hula hoop. The thing is, the light that's coming off of that material, as it tries to escape, the black hole is actually bending it towards us. So what you're seeing here is actually the back of that accretion disk. And that light from the back of the accretion disk is bending over the top and over the bottom, which is why it looks like there is a circle here. I'm going to link to exactly what you're seeing in a Veritasium video, and Derek does a pretty good job of explaining what the heck this is a photograph of. Alright, so the first way that we know is because we actually have a real photograph, an actual photograph of a black hole. The second reason that we know is because as that material is falling in and it heats up, it ionizes the gas and it creates those jets that we talked about. Those jets, if they are pointed towards planet Earth, are the brightest objects in the sky. The brightest event is a supernova, but the brightest sustained object is those jets if they are pointed at Earth, and we call those a quasar. We can see quasars from the other side of the galaxy. Quasars are not the black hole itself, but they are the jets that are coming out of the North Pole and the South Pole of the magnetic field. And then the final way is gravitational lensing. Because they have so much gravity, they are going to bend space-time. So there is something behind the black hole giving off light, and that light is bent. We can actually determine that there is a black hole between that object and us. So as a black hole travels through the universe, the light from behind that black hole is going to get bent. Another question is, how do we know how massive they are? How big are they? We can find the mass of a black hole by studying things that are near it that it has an effect on that we can see. Just like you can have a planet orbiting around a star and it causes that star to wobble a little bit. Well, you can actually have a star orbiting around a black hole, and that star is going to seem to move. Here we have a star that is in orbit around a black hole. You can change the mass of the black hole. If you increase the mass, it's going to speed up the star, and it's going to cause the black hole to wobble a little bit less. If you decrease its mass, you're going to slow down the star, and the black hole itself will start to orbit this common center of gravity between the two. And based on the orbit of the star that we can see, we can actually calculate how big that black hole is. So by measuring the speed of the star, you can calculate the exact mass of the black hole. In this case, the star was going 118 miles per second, so the black hole is about 10 times bigger. Let's change it to somewhere here. We measure the speed of the star that we can see, and we get 243 miles per second. Based on the speed of that star, we can then calculate that the mass of this black hole is about 40 times. So by looking at things that we can see, we can calculate the mass of a black hole. Now what everybody wants to know, what happens if you fall into a black hole? Well, this is what it would look like. As you fall into a black hole, all of the light from every direction is going to start going in the same direction as you. You're also going to start catching up to that light because your speed is increasing. And when you are catching up to that light, you're going to start to become blue shifted. So the light that you're seeing is blue shifted. So as you fall into a black hole, you start seeing light from all different parts of the universe, from all directions, going in the same direction as you, and then you are catching up to that. As you get closer to the singularity, all of the light from everywhere is going to be kind of right in front of you as you catch up, and you're just going to see this bluish dot in front of you that is light from the entire universe. Weird to think about. In order to talk about what's going to happen to your body, though, you need to know about relativity. Basically, Einstein tells us that time and space are relative. They're not fixed. You can bend space, and time can speed up and slow down, depending on if you are moving, also depending on if you are near things with a lot of mass. Things with a lot of mass, like a star, even a planet, are going to cause distortions in space and time both. So a black hole is going to cause a huge distortion in space and time. We're starting to get into Einstein's special relativity, which is basically his idea of how gravity works. It's a little bit complicated, but hopefully this will help.
Number 10, special relativity. Does time fly when you're having fun? In 1905, Albert Einstein introduced the theory of special relativity, which said that if the speed of light is constant, then people must experience time differently. Which may sound impossible, but Richard Feynman later showed that you can prove it with just lights and mirrors. If you set up two mirrors, one of which had a flash bulb and a detector on it, you could build a clock which ticked every time the flash was reflected back to its original source. It would keep time perfectly, though it would make a slightly annoying alarm clock. But if you make this clock go past you very quickly, the light has further to travel, and since light always travels at the same speed, the moving clock runs slower than when it was at rest. So though time might not fly when you're having fun, a moving clock does tick more slowly than the observer's stationary clock, which may have changed the way we see the universe, but doesn't always make for a good excuse.
A black hole has so much mass. As you approach it, time is actually going to start to slow down for you. So the closer you get to that black hole, the slower time is going to seem to run. If you had a clock on you, this is what it would look like. As you are falling towards this black hole, a few things will happen. One, somebody looking at you is going to see their clock just continue to be normal, but your clock, because time is starting to travel slower, when you are looking at your clock, it's going to start to slow down. The second thing that's going to happen to you, while you see everything blue shifted, the light that is coming from your body to that observer's telescope is going to start to be pulled by that black hole. And if it's pulled by that black hole, it's going to get stretched out and become redshifted. So an observer is going to see two things as you fall into the black hole. They're going to see your clock slow down because time starts to slow down for you. They're also going to see you start to turn red until eventually, as you cross that event horizon, no light can travel, and the last thing they see from you is the light that was given off just as you reach that event horizon. Let's watch what that's going to look like.
1, 2, 3.
The voice is
4,
going with this
5,
clock.
6, 7, 8, 9, 10,
11, 12, 13, 14, 15.
We're going to drop the clock
1,
into the black hole,
2,
and
3,
it is counting off
4,
the seconds
5,
of the clock
6,
dropping into the black
7,
hole.
8.
This clock is going to start
9,
to slow down.
10, 11,
As it slows
12,
down, it's also going to start to look
13,
redder and redder and redder.
15.
Until eventually the clock seems to stop, and the last image that you see of something falling into a black hole is that object in very stretched out light, and you're going to look red shifted. That's what somebody sees when they watch you fall into a black hole. Your time seems to slow down and you turn kind of red as the light is stretched out. But what do you feel? What is happening to your body? Let's go back to gravity. Remember that gravity is affected by how far away you are from an object. The reason that we don't fly off of the Earth into the sun is because we're closer to the Earth, so we feel Earth's gravity much stronger. Well, when you jump into a black hole, let's say you jump feet first, the part of you that is closest to that black hole is your feet. And so what part of your body is going to feel the most gravity? Because it's the closest, your feet are. What part of your body is going to feel the second most gravity? Your knees. What's going to feel the third most? Your waist, and then your shoulders, and then your head. The gravity of a black hole is so intense that the force of gravity that your feet feel is so much stronger than what your knees feel that your feet actually get pulled off of your knees. And then your knees are closer than your waist. But again, gravity is so much stronger at your knees than your waist that your knees get pulled away from your waist. This is that tidal effect that we talked about, where the closer you are to an object, the stronger gravity you feel. When you jump in, the closest part to the black hole feels the strongest gravity. The farthest from the black hole is going to feel the least amount of gravity. And you are actually going to get stretched out as time goes on. The closest part to you is going to get pulled more than the farthest away part. And your body will get stretched out, or your spaceship, the closer parts, will get pulled into the black hole before the back of your spaceship. And this phenomenon is what is known as spaghettification, because you get pulled apart like a big piece of spaghetti. And your feet will get pulled off of your knees get pulled off of your waist will get pulled off of your shoulders, and then the cells in each one of your body part will get pulled apart, and then the atoms inside of your cells will get pulled apart, and you will actually enter the singularity as a stream of particles, not as a person. You're going to get stretched out like a piece of spaghetti. Black holes don't last forever. They actually evaporate. And already you're like, wait a minute, how is a black hole supposed to evaporate if nothing can escape it? The reason is because of what's known as Hawking radiation, named after Stephen Hawking. Hawking radiation has to do with virtual particles in empty space. A virtual particle is a pair of particles that just pop into existence. You have a particle and an antiparticle. And as soon as they form, they touch and they annihilate one another. And all over the entire universe, these virtual particles are popping into existence and then annihilating, and they're gone again, turning back into energy. This is one of those weird things that quantum mechanics tells us happens, even though it doesn't make sense to us. Well, if you have a particle and an antiparticle that pop into existence right on the event horizon of a black hole, the particle can fly away, the antiparticle gets pulled in. That antiparticle, instead of causing its little particle pair to disappear, is going to get pulled into the singularity and cause a little piece of mass in the singularity to disappear. Meanwhile, this particle is going to fly out from the black hole, and it's going to seem to an outside observer as though this black hole just let go of this particle. This particle is what's known as Hawking radiation, and it has to do with these particles and antiparticles popping into existence right on the event horizon of a black hole. So how fast does it take for a black hole to evaporate? Well, if you're small, you don't have a lot of stuff in you, so it only is going to take a little amount of time to evaporate away. The big ones, though, can take up to a Google years. A Google is what the search engine was named after, but a Google is spelled a little bit different. It's a 1 with 100 zeros after it. So a billion has 9 zeros, a trillion has 12, quadrillion has 15. 100 zeros, that is a very long time. So these supermassive black holes, they do evaporate because of this Hawking radiation, but the time that it takes for a black hole to evaporate, like red dwarfs will long since have died, become white dwarfs, and then black dwarfs. Like, it's way past that, way in the future. It's hard to, I'm starting to get speechless. It's a long ways away. Just, it's in the future. A Google use from now. Here's Brian Greene, who's the #1 string theorist on the planet, telling us about Hawking radiation.
Hawking radiation is a very subtle feature of black holes that only comes to light when you go beyond Einstein's general theory of relativity and include some effects of quantum mechanics. The idea is this. At the edge of a black hole, where quantum mechanics operates, as it does everywhere else, there can be what we call quantum fluctuations, which are productions of particles that really pop out of the nothingness, exist for a fleeting moment, and then find each other and annihilate and no longer exist. The strange thing that can happen at the edge of a black hole is that when these particles are produced, one can get pulled into the black hole, leaving its partner free to fly off into space. And that particle that flies off into space is something in principle that we could see. It's radiation that comes from the edge of a black hole. So in essence, when you take quantum physics into account, black holes aren't completely black. They can radiate from these quantum processes, radiation that's called Hawking radiation.
If everything that I just said confused the crap out of you, this is Brian Cox explaining to Joe Rogan what a black hole is, and he's much better with words than me.
There's a supermassive black hole at the center of every galaxy.
Yeah.
But there's also other black holes that aren't necessarily in the center of galaxies.
Yeah, so these little ones, well, little,
Little.
they're a few times the mass of the sun, and they're from collapsed stars. So they are stars at the end of their life, very bigger than the sun, more massive than the sun, but they run out of their fuel and they start to collapse because gravity squashes them. And if they're sufficiently massive, then there's nothing that can stop the collapse. And so they collapse, as far as we know, to a point, right? Essentially an infinitely dense point. We don't really know what happens we don't know what happens right in the middle. But they collapse to such an extent that there's a region around it from which light can't escape. And so nothing can escape. And that's a black hole.
And what happens to them? Do they travel? Are they moving through space?
Yeah, they're still stars,
right?
So they're still there. They're surrounded this region where if you fall in, it's called the event horizon, And if you go across that horizon, then you are going to the center. There's one way of thinking about it, which is quite cool, which is that the time and space sort of flip is one way to think about it. So in the same way that we are going into the future now, so we're going to tomorrow. There's nothing we can do about it. We are going to tomorrow. In the same way, if you fall in across the event horizon of a black hole, you are going to the middle, the singularity it's called. So that's your future. Every line of your future points to the center of the black hole. So it's kind of the ultimate of no escape, the ultimate prison. You're going to get squashed to an infinitely dense point.
Not every star becomes a black hole at the end of its life?
No, because if something like the sun...
we have a small star.
It's quite small, yeah. And when it collapses, there's a sort of a pressure, a force, if you like, which is caused by the fact that electrons don't like to be very close to each other. So it's called the Pauli exclusion principle. But essentially what happens is that, so as they get squashed closer and closer together, they move faster and faster to sort of get out of each other's way, if you like. And that makes a force which holds them up. And so that creates what's called a white dwarf star. So you can have a blob of matter. They're about the size of the Earth, but they're about the mass of the sun. And so that's for smaller stars. They end up as these white dwarf things, which are very dense objects. There's another version, which is called a neutron star, which is the same thing, but for neutrons. And they move faster and faster. So if it's massive enough that it overwhelms the electron thing, then the electrons sort of crush into protons and turn into neutrons, and the whole thing starts again. And so a neutron star can be, at least 1.5 times the mass of the sun, let's say, but it can be about 10 miles across. So that's an incredibly dense ball of matter held up by the neutrons moving around. It's got a fancy name. It's called neutron degeneracy pressure, but that's what it is. But if you go even bigger, then even that can't hold it up. And as far as we know, then there's no known force that we know of that can hold the thing up if it's too massive. And so that's when it just almost winks out of existence, if you like. It collapses and collapses and collapses, and that's when you get a black hole.
We try to put that into perspective. The sun is 1 million times bigger than the Earth.
Yeah.
And this neutron star is, would you say, 1.5 times the mass of the sun,
so
but 10 miles wide?
Yeah. So, and there's loads of those around. They're called pulsars. So we see those all over the place. The first one that was discovered was called LGM1 because they spin very fast. And it was called LGM1 because it's a very regular pulse, and they thought it was little green men. So they called it kind of jokingly Little Green Men 1. And so, yeah, we've seen that there's one called the Crab pulsar, which is in the Crab Nebula, which we saw the supernova explosion. So that's when one of these stars explodes at the end of its life and then collapses to form a neutron star. And we saw that in 1054 AD.
Here's another Kurzgesagt video telling us just how weird black holes really are.
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about 1/4 of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014+81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. When it arrives at the mass of a large asteroid, it's radiating at room temperature. When it has the mass of a mountain, it radiates with about the heat of our Sun, and in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. But this process is incredibly slow. The biggest black holes we know might take up to a googol years to evaporate. This is so long that when the last black hole radiates away, nobody will be around to witness it. The universe will have become uninhabitable long before then. This is not the end of our story. There are loads more interesting ideas about black holes. We'll explore them in part 2.
And this is a Kurzgesagt video telling you what would happen if you had a black hole in your pocket.
What would happen to you if a black hole the size of a coin suddenly appeared near you? Short answer, you'd die. Long answer, it depends. Is it a black hole with the mass of a coin, or is it as wide as a coin? Suppose a US nickel with a mass of about 5 grams magically collapsed into a black hole. This black hole would have a radius of 10 to the power of minus 30 meters. By comparison, a hydrogen atom is about 10 to the power of minus 11 meters. So the black hole compared to an atom is as small as an atom compared to the Sun. Unimaginably small. And a small black hole would also have an unimaginably short lifetime to decay by Hawking radiation. It would radiate away what little mass it has in 10 to the power of minus 23 seconds. Its 5 grams of mass will be converted to 450 terajoules of energy, which will lead to an explosion roughly 3 times bigger than the atomic bombs dropped on Hiroshima and Nagasaki combined. In this case, you die. You also lose the coin. If the black hole had the diameter of a common coin, then it would be considerably more massive. In fact, a black hole with the diameter of a nickel would be slightly more massive than the Earth. It would have a surface gravity a billion times greater than our planet currently does. Its tidal forces on you would be so strong that they'd rip your individual cells apart. The black hole would consume you before you even realized what's happening. Although the laws of gravity are still the same, the phenomenon of gravity that you'd experience would be very different around such dense objects. The range of the gravitational attraction extends over the entire observable universe, with gravity getting weaker the farther away you are from something. On Earth right now, your head and your toes are approximately the same distance from the center of our planet. But if you stood on a nickel-sized black hole, your feet would be hundreds of times closer to the center, and the gravitational force would be tens of thousands of times as large as the force on your head and rip you into a billion pieces. But the black hole wouldn't stop with just you. The black hole is now a dominant gravitational piece of the Earth-Moon black hole of death system. You might think that the black hole would sink towards the center of the planet and consume it from the inside out. In fact, the Earth also moves up onto the black hole and begins to bob around as if it were orbiting the black hole, all while having swathes of mass eaten with each pass, which is much more creepy. As the Earth is eaten up from the inside, it collapses into a scattered disk of hot rock surrounding the black hole in a tight orbit. The black hole slowly doubles its mass by the time it's done feeding. The Moon's orbit is now highly elliptical. The effects on the solar system are awesome. In the biblical sense of awesome, which means terrifying. Tidal forces from the black hole would probably disrupt the near-Earth asteroids, maybe even parts of the asteroid belt, sending rocks careening through the solar system. Bombardment and impacts may become commonplace for the next few million years. The planets are slightly perturbed, but stay approximately in the same orbit. The black hole we used to call Earth will now continue on orbiting the Sun in the Earth's place. In this case, you also die.
And finally, probably one of my favorite YouTube videos that I've ever watched in my life. This is Vsauce explaining what would happen if you fell into a black hole.
Hey, Vsauce Michael here, and today we are going to go inside a black hole. It's not going to be comfortable, but it will be pretty fun. Now, first things first, mathematically speaking, anything could become a black hole if you were to compress it into a small enough space. That's right, you, me, this camera, everything in the universe has what is known as a Schwarzschild radius, a tiny amount of space that, were you to collapse the entire mass of the object into, its density would be so great that its gravitational pull would be so great that not even light could escape from it. You would have a black hole. If you were to compress Mount Everest into something smaller than a nanometer, you would have a black hole. And if you were to compress the entire Earth down to the size of a peanut, you would have a black hole. But fortunately for us, there is no known way to compress Everest or Earth in that fashion. But a star, many times larger than our own sun, has a much larger Schwarzschild radius. And when it runs out of fuel and can no longer keep itself hot enough, it collapses to a single infinitesimally small point known as a singularity. Its density will be infinite, and so its gravitational pull will be so strong that nothing can escape, not even light. But enough about ways black holes form, let's jump into one. First question, what would it look like from the outside? Well, we know that gravitational fields bend space and time. Stars behind our sun will actually appear to be in slightly different locations from Earth because the sun's gravitational field bends the light coming from those stars. When it comes to the gravitational fields of larger objects like entire galaxies, or for that matter a black hole, the effect is even nuttier. Light coming from objects behind them is significantly distorted, producing smears and smudges. As seen from Earth, the blue galaxy behind this red galaxy is completely distorted, like a funhouse mirror. So rather than appearing as it really should, it looks to us like a ring, a smudge all the way around the red galaxy. This is known as gravitational lensing. Now take a look at this simulation of a black hole with a galaxy millions of light years behind it. The galaxy's not really in danger of the black hole's suck, but the light coming off of that galaxy certainly is. Watch as the galaxy passes behind the black hole, and its light is contorted, twisted, and distorted. Now here's a really fun demonstration. What if the Earth were to orbit around a black hole? Looking from the outside, the Earth would look normal at first, but as soon as it passed behind the black hole's gravitational field would warp the light reflecting off the Earth, producing this. For the sake of simplicity, let's jump into a simple black hole, one that doesn't have a charge and isn't moving, and also isn't already sucking up a bunch of matter, so it's just there on its own. As we approach, the distortion of the sky grows greater and greater. A larger and larger portion of our field of view looking forward into the black hole will be filled with darkness. At this point, where half of our field of view has been swallowed up in darkness, we have reached the photon sphere. At this point, light is not going to necessarily get sucked into the black hole, but it doesn't necessarily leave it either. Instead, at this magical point in space, light, photons, can actually orbit the black hole. If you were to stop here for a moment and look to the side, you could theoretically see the back of your own head, because light reflecting off the back of your head would travel all the way around the sphere of the black hole right back to your face. A gravitational field not only warps space, it also warps time. Now, for most intents and purposes here on Earth, we never have to worry about that. But near a black hole, gravity would be so strong that an observer standing, watching you jump into the hole, would see something quite strange. They wouldn't see you get sucked quickly into the hole. Instead, they would see your approach become slower and slower and slower until you reached a point known as the event horizon. This is a point in space where, once crossed, there's no going back. It is at that point that light can no longer escape. And so to a person watching you fall into the hole, that would be where your journey ended. You would seem almost frozen in space, the light coming off your body becoming increasingly red-shifted until you simply faded into nothingness. They would never see you cross the event horizon. But for you, of course, everything would seem fine and dandy. You would continue past that horizon to your now inevitable death. As you continue to approach the black hole's singularity, your view of the entire universe would get compressed into a smaller and smaller point in space behind you. If the black hole we're jumping into is large enough, things might actually be quite comfortable at that event horizon. We'll know that we're never going to escape and that our lives are pretty much over, but it might take us hours to actually reach a point where things started to hurt. Why would they hurt? Well, the closer you get to the singularity, the more significant the difference in gravitational pull is across space. And so parts of me that are closer to the singularity would be pulled more strongly than parts that were facing away, and my entire body would be stretched toward the singularity. The effect would be so incredible, scientists don't usually call it stretching, they call it spaghettification. Once you reached this point, you would be dead. Your molecules would be violently ripped and stretched apart, and when they got to the singularity, well, we don't really know what would happen. Perhaps they would completely disappear in violation of all the laws of physics, or maybe they would reappear elsewhere in the universe. It's believed that a moving or spinning black hole might actually create what is known as a wormhole, a way of transitioning across space faster than light. Not in any way that violates the laws of science, but in a way that takes advantage of the universe's dimensions. For instance, if I wanted to get from this point to this point, I'd have to travel the distance. But theoretically, a wormhole would do something really crazy. For instance, this. Now, the 2 points are right next to each other and I can travel between them almost instantaneously. But again, this is all theoretical. Luckily, we do have a possible way of analyzing black holes right here on Earth. Enter the dumb hole. Just as a black hole does not permit light to escape, a dumb hole is an acoustic black hole. It won't allow sound to escape. It doesn't have to be nearly as powerful, and scientists have been able to create dumbholes in laboratories using special fluids traveling at the speed of sound. A lot of progress still needs to be made in the world of acoustic black holes, but we may be able to learn an amazing amount of information about how black holes work by looking at how sound is treated in a dumbhole. Now here's another good question. What would it look like to travel at the speed of light, say, toward the sun? Well, surprisingly, you wouldn't just see the sun immediately rush up toward you. No. In fact, initially, it would look almost as if the sun were receding away from you. Why? Because your field of view would vastly increase in size. You would be able to see stuff almost behind you, and here's why. As you sit there, not moving yet, looking at the sun, there's light coming from stuff behind you. But if you travel the speed of light, you will actually reach that light coming from things behind you. As you reached light speed, your field of view would expand like this, concentrating the stuff in the middle. But where are you in the universe? Or here's a better question, where is the center of the universe? Well, this might sound crazy, but it's everywhere. This is known as the cosmological principle. No matter where you are in the universe, everything else will seem to be moving away from you, expanding at the same rate. The universe is expanding, but not like a balloon getting bigger with all the people inside it. Instead, it's as if we are the surface of a balloon. If you were to put a bunch of dots on a balloon and then blow it up, all of the dots would move away from each other at the same rate. And on the surface of the balloon, there is no center. Take a look at these two layers. They are exactly similar, except the top layer represents a 5% expansion of the bottom layer. Let's say that you live on one of these dots, and you want to measure where everything's moving away from. Well, watch what happens when I line up a dot in the past and the present. Boom. It looks like the center of the expansion. I can do this with any dot. As soon as I choose a dot to be the frame of reference, it immediately becomes the center of the expansion. So while dying in a black hole would be lonely and scary and morbid, when you look up into the sky, think instead about this. No matter where you are or who you are or what your friends or your parents tell you, you really scientifically are the center of the universe. Finally, what if our universe was a Googleplex meters across? It is nowhere near that large, but if it was, it would be so voluminous that statistically, it would be nearly impossible for there not to be an exact copy of you somewhere else out there in the universe. To see why, I highly suggest that you click right there and check out Brady Heron's new channel, Numberphile. It's part of the YouTube original channels, and I've worked with these guys before. They're amazing. They're my favorite kind of geeks. So check out that video, watch their other stuff, and if you like math, I highly suggest that you subscribe. And as always, thanks for watching.
Black holes are some of the most fascinating, mysterious, and downright strange objects in the universe. They have such strong gravitational pull that anything that gets sucked into a black hole disappears forever. Even light cannot escape the clutches of a black hole. We know that nothing ever comes out of a black hole, but what happens to the stuff that does fall in? What's actually inside a black hole? Scientists have long been fascinated with black holes. The existence of objects with gravitational fields too strong for light to escape has been theorized about the greatest scientific minds since as far back as the 18th century. After Einstein developed his revolutionary theory of general relativity in 1915, scientists finally had a way to calculate and describe the phenomenon of a region of space from which nothing can escape. Still, the existence of black holes remained a mere mathematical curiosity until the 1960s, when Stephen Hawking popularized the concept. Until very recently, the only way we've been able to find black holes is by combing the skies for the telltale signs of their interactions with nearby objects. Gases and stars near a black hole behave differently than elsewhere in the universe, affected by the black hole's gravity and giving off a high-energy light invisible to the naked eye but detectable with telescopes using special tools. Through reverberation mapping, scientists can measure the radiation thrown off by a rotating disk of debris around a black hole and pinpoint its location, even if they can't see the black hole itself. Then, in 2019, scientists did something that was previously thought to be impossible. They captured an image of a black hole using the International Event Horizon Telescope. Finally, the world had solid photographic proof of the existence of black holes. Technically, what they captured was the black hole's shadow, since the black hole itself does not reflect any light, but nevertheless, it was a major breakthrough that would have thrilled Einstein just a century ago. Despite our inability to get near one or even to see one with our own eyes, thanks to the tireless and groundbreaking work of mathematicians and theoretical physicists, we've been able to learn quite a lot about the formation, properties, and behavior of black holes, even before we were able to view them with the help of technology. A black hole is a place in space where the force of gravity is so strong that nothing can escape from it, not even light. The gravitational pull is so strong because in a black hole, all matter has been squeezed into an inconceivably tiny space. Mass refers to the amount of matter or stuff in an object. The smallest black holes, which were believed to have been created at the time the universe began, might be as small as a single atom, but they have the same mass as a large mountain. Stellar black holes, created when the center of a large star collapses in on itself in a supernova, can have a mass up to 20 times greater than our Sun. The largest ones, called supermassive black holes, have masses greater than 1,000,000 of our suns and lie at the center of every galaxy in the universe. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A, has as much mass as 4 million of our suns, all condensed into only a ball as big as a few million Earths. If our sun were somehow replaced by a black hole with the same exact mass, would the Earth be in danger of falling into the black hole, never to be seen again? The black hole's gravitational pull would be identical to the sun's, despite the fact that it would be much smaller. The Earth and the rest of the solar system would continue to orbit the black hole the same way they orbited the sun, though without the heat and warmth they're used to from the sun. Thankfully, our sun is not massive enough to collapse into a black hole, so it's not something we have to worry about. If we're able to know so much about how black holes form and what happens around them without having visited or even seen one, can we possibly have any clue what's actually inside a black hole? Though it would seem impossible for anyone who somehow made it into a black hole to report back to us, scientists do have some pretty good ideas about what goes on inside a black hole. The closest black hole to Earth is more than 1,000 light years away, so unfortunately, it doesn't look like we'll be sending any exploratory missions there anytime soon. But if we could, what would we find out? What would the first brave explorers see inside a black hole? Anyone brave enough to get near a black hole wouldn't actually be able to see it as they approached. The objects outside of the black hole can fall into it, effectively impacting whatever is inside, but the black hole cannot affect the exterior universe because its gravitational pull is so strong that anything sucked inside, including light, can never escape. If light cannot escape, there is nothing for our eyes to see when we look at a black hole. Instead, explorers approaching the black hole would have to be on the lookout for the cloud of gas and debris orbiting it to know they're close. As the brave explorers drew closer and closer to the black hole, they would notice a threshold beyond which there is nothing but an empty, black nothingness. This is the event horizon, the black hole's last frontier and the point of no return. A black hole itself is a singularity, a point of infinite density, where all matter has been squeezed into an infinitely tiny space and the laws of physics cease to apply. The singularity is shrouded from view by the event horizon, what we would consider to be the surface of the black hole, though it's not a surface in the true sense of a word. The event horizon is not a real physical barrier or a membrane, but rather it's an invisible barrier at a particular distance from the singularity, a threshold beyond which the gravitational pull is so strong that nothing, not even light, can escape. Once something or someone has crossed the event horizon, there is no going back. Once they've pierced the veil, they'll begin the long fall toward the singularity, the ultimate one-way trip. The fall into the black hole wouldn't be instant. A brave explorer would have a few moments to enjoy the experience. The time it takes to reach the singularity after crossing the event horizon depends on the size of the black hole. In the smallest of black holes, like one the size of a few of our suns, it would take less than an eye blink to reach the singularity. But in a massive one, millions of times larger than the sun, the explorers would have a few heartbeats in which to take in their surroundings. What they would see and experience in those few brief seconds would seem like something straight out of a sci-fi movie. In the universe outside of a black hole, objects and people are free to move in any direction they choose, up, down, left, right, backwards, or forwards. But they are always moving forward through time. Inside the event horizon, though, there is no other option but to travel toward the singularity. Inside a black hole, the singularity is the future, and all matter that falls into a black hole must simply travel toward it. No matter which direction someone in a black hole is traveling or which way they turn, the singularity is somehow always right in front of them, while at the same time always out of sight. As the daring explorer falls forward beyond the event horizon and is drawn toward the singularity, they would find that the space around them is anything but black. In fact, they'd be completely enveloped in light from the surrounding universe, light that crossed the event horizon and is falling toward the black hole along with them, doomed never to escape. The extreme gravitational forces inside the event horizon would bend and twist the light as it gets pulled toward the singularity. Those same gravitational forces would be hard at work on the explorer's body too. The black hole's tidal forces would exert different amounts of gravitational pull on different parts of the body, squeezing it at the midsection and pulling and stretching from end to end, in a process appropriately dubbed spaghettification. As the explorer's body is stretched, infalling light would be concentrated into a band of light wrapped around their waist, until both body and light lose all dimensionality. If the heroic explorer could peel their eyes away from their body's physics-defying acrobatics, they would witness another strange phenomenon: time dilation. The universe they left behind beyond the event horizon would still be there, but would appear to have sped up and be moving much faster than the time inside of the black hole. But to anyone looking on from the outside, they would see something much different. To them, as the explorer began to approach the event horizon, they would have appeared to move slower and slower, and it would look like they never crossed the event horizon or fell into the black hole at all. When the falling explorer finally catches a glimpse of the singularity, they would see, well, nothing. Reaching the singularity would feel like landing on the surface of an enormous, empty, featureless black planet stretching from horizon to horizon. The explorer's body, by now distorted beyond all dimensionality, would be crushed into a tiny ball of infinite density before dissolving irrevocably into the singularity, never to be seen or heard from again. All that they've seen and all they've experienced inside the black hole would be dissolved with them, lost to us forever. Those on the outside could certainly attempt to send signals into the black hole, but those signals would only join the explorer's body in the singularity. Even if someone inside a black hole could somehow receive the signals and attempt to reply, the black hole's intense gravity would ensure that no information would be able to escape the black hole. At least whatever dirty secrets the explorer took into the black hole with them would be safe forever. It's truly awe-inspiring to realize that we've only recently gotten photographic proof of a phenomenon that's been theorized about for centuries and mathematically proven for 100 years. Even more incredible is the fact that as much as we know about black holes, we have yet to see inside one. Everything we think we know about what's actually inside a black hole is still purely mathematical theory and conjecture until we can figure out how to get a real look inside and live to tell the tale. That doesn't seem likely anytime soon, but science continues to surprise us, so we might just find out sooner than we think. If this video hasn't scared you off of space exploration, you'll have to check out What It Takes to Join Space Force, or if you prefer to remain on terra firma, you'll like this other video instead.
In your own words, I want you to tell me what a black hole is and what would happen if you fall into a black hole.